SwayamPrabha. Digital India. Educated India.
In this lecture, one of the most important point we'll be discussing, which is equilibrium point or trim point or fixed point, we say from the different perspective. Based on the equilibrium point, how we can define the stability of the system. So there are two types of stability we'll be discussing in this lecture. One is static stability and another is dynamic stability. How the system going to behave with respect to equilibrium point. That is part of the static stability, and dynamic stability basically how the system behaves with time, a time history of the system. And we'll be discussing this part from the trajectory as well, how the system, it means the aircraft system evolves over time. And then we'll conclude the lecture. Now let's discuss on the equilibrium point. Equilibrium point. Let's consider we have system x star equal to f of x u t. Let's assume this is any dynamical system and dynamical system. And if this system does not affected by any contour, if it is does not affected by any contour u, or we can write u equal to 0. In that case, we can write x dot equal to f of x 0 t. And if you assume the solution of this equation, the solution of x dot equal to f x 0 t be x star some constant value, the point x star is said to be equilibrium point if it has the property that whenever the state of the system x, so x is basically changing with time, but x star is basically here equilibrium point, it's constant value, but once the system evolves over time, the x will change. So now whenever the state of the system x starts at x star, it will remain at x star for all future time or future state. If this condition hold, then we can say the system is in equilibrium state. So this is basically a desirable property when designing and implementing. So I can say this is uh, desirable property while implementing control system. So in control system, our main motivation is to maintain the system at the equilibrium point. Here, we'll assume, since you'll be assuming the system in this course are LTI system, so we can assume the equilibrium point always zero. We shall consider the LTI system with equilibrium point at the origin. X. So we can, if you look this, let's assume we have system x dot equal to minus 4x. And we have some kind of force or torque in the system. Let me assume U. So as per the definition, we have to consider U, the control or some force to be zero to find the equilibrium point. So we need to put U equal to 0 and x dot equal to minus 4x. And in the equilibrium condition, we assume the x star is a constant value, as you mentioned, the constant value. So in that case, we can write the rate of change of the state to be zero. So here to find equilibrium point, dx dt, you can make it to zero. And from this minus 4x equal to 0, so x equal to 0. So in this case, x star is 0. We can assume equilibrium point. Equilibrium point. So in LTI system, most of the LTI system are equilibrium point is assumed to be zero at origin, x star equal to 0. So now we'll shift our attention how we can look this concept of equilibrium point for an aircraft. Let me write. Let's discuss the stability, because we'll define the stability of the system about the equilibrium point of the system. Here system basically aircraft with respect to if an airplane is remain in steady uniform flight, so it means the total force and moments acting on the system or in the aircraft is assumed to be balanced about CG. So in this condition, the resultant force and moment about CG, center of gravity, must be equal to 0. So it means if the aircraft satisfying this condition, we can say that the aircraft is in the state of equilibrium or at a stream condition. So if the aircraft satisfying this condition, we can say the aircraft is in the state of equilibrium or flying at a stream condition. So these are the desirable properties for an aircraft. And In the other hand, if the resultant forces and moments are not summed to zero, then the airplane will go through some motion, which is basically translational motion or rotational motions. On the other hand, if the total forces and moment acting on the system are unbalanced, balanced, then the aircraft will be subjected to translational or rotational motions. Based on this, we can come up with two important parts in stability, how the system evolves over time. And based on this definition, the stability of an aircraft can be divided into two parts. Based on the equilibrium conditions. So the stability of the aircraft parts with respect to equilibrium point. The first is static stability, and another is the dynamic stability. So let's start with the static stability part. Under static stability, we'll check whether the system has initial tendency to return to the equilibrium point after a disturbance is being applied. So let me define it. Static stability is the initial tendency of the aircraft to return to its equilibrium point after a disturbance let's look some representation how we can the static stability can be defined. So let's assume we have curved surface here, and let's assume this is the initial position of the ball on this curved surface, and if you apply some disturbance on this ball, and let's assume the balls after the disturbance has been shifted to here. Now, after some time, the ball will come back to the equilibrium point because there is some restoring force acting on this ball after it being disturbed from the equilibrium conditions. This is the ball's equilibrium conditions. So if this kind of phenomena happens in the dynamical system, and this kind of motion, we can say, or we can say this point, this is the point or state of the system, we can say static or stable equilibrium point. because the ball has initial tendency to back to the equilibrium condition. So this is my equilibrium condition. So if the ball is disturbed from this equilibrium point, it will be coming back to the equilibrium point again due to some restoring force acting on the system. So this is we call stable equilibrium point, or the system we can say statically stable system. If we consider another surface like this, and let's assume this is the equilibrium point, and if you disturb the body or this point, and after the disturbance, let's assume the ball position is here. So if you see carefully, after the disturbance, the ball has no tendency to come back to this point, initial point. So if the system has this kind of phenomenon, we can say the system is statically unstable. So this is, we can say, statically stable. And also we can say unstable equilibrium point. And let's look another condition. We have surface, and let's assume the initial position of the vehicle is somewhere here, and after the disturbance, let's assume the vehicle position is here. And if you notice, even the body is perturbed or disturbed from this point to this point, this will be, again, it will stay in this point for all future time. And if the system has this kind of property, we call the system is neutrally stable. And this property is called neutrally stable. And the equilibrium point is neutrally stable equilibrium point. So from this example, we can conclude that if you are having a stable equilibrium point, we can say the vehicle must develop a restoring moment or force to bring the vehicle to the equilibrium point. Now let's extend this concept for our aircraft. Let's assume the vehicle initial position is here, and if you are having the system, if the system has initiated some turbulence, it goes through some nose down motion, but after some time it come back to again the same trajectory what you have initially. And if the vehicle has this kind of system properties, and we can call this aircraft is statically stable aircraft. Now if we have another condition here, let's assume the vehicle initial position is here. If there are some turbulence acting on the system and it deviates from the initial position, and it continues to diverge from this from the initial position, and the vehicle has this kind of tendency, we call the system or the aircraft is statically unstable aircraft. Now we have another conditions. If the vehicle is initially here, and due to some perturbations on the system, it comes to here. Again, some perturbation system coming to here. And if you look carefully, the body continues to be in the same line. And if the vehicle has this kind of tendency, we can call the system is neutral stable. Neutral stable. Now we'll extend the concept of dynamic stability, how we can define the dynamic stability of a system. So dynamic stability basically how the system behaves over time. So let me write dynamic stability. So here mostly we are concerning how the system behaves over time. Here we concern with the time history of the vehicle after it is disturbed from the equilibrium point. From the equilibrium point. So this is very important property for designing control system, because for designing control system we'll be looking how the system going to behave over time. So let's look some phenomena how dynamic stability occurs. Let's assume we have the displacement of the aircraft, how it evolves over time. This is my time axis and this is displacement of the aircraft. Let's assume we are starting from here. If the vehicle over time follows this kind of response, then we can call the system is exponentially stable. Exponentially stable. And if you have another kind of response, suppose this is time axis and this is my displacement axis. If the system starting from here, for example, and if you have the system response over time, something like this, then we can say the system is diverging over time. Diverge over time. And if you have another kind of response, this is my displacement of the aircraft, this is time, and if the system behaves like this, then we can say this is neutral stable. And if you have something like this kind of properties, this is my displacement, this is time axis. If the system starts from here, and with time, if it is oscillating, and after some time, if it is converging to the equilibrium point, in this case, we are assuming the equilibrium point is 0, the displacement. And if you have such kind of response in the system, this is kind of response we call damped oscillation. Damped oscillation. Because the system is, over time, it is due to the damping, it is the oscillation in the system going out and it is converging to the equilibrium point. And if you're having the response something like this, in this figure, this is my time axis, this is my displacement axis, And if the system starting from here, and if it is over time, if it oscillating like this, it is basically the system is going with same magnitude of oscillation, then we can say this is undamped oscillations. Because if you look, the response remains to be same over time, same magnitude of the same frequency of the oscillations. So this kind of response we call undamped oscillations. And if you have something different kind of response with time, this is my displacement, this is the time axis, and if you look, the response is like this, something like this. If you look carefully, the magnitude of oscillation is increasing with time, and if the system has this kind of behavior, we call divergent oscillation. Divergent oscillation. So this is how we can see how the dynamic stability in the system occurs. In this course, we'll be mostly talking the dynamic stability of a system over time. And this is a very important part for designing the autopilot of a vehicle. In the next lecture, we'll be talking on the dynamic stability of our nonlinear system. And in that lecture also we'll be discussing how we can find the equilibrium point of our nonlinear system. And based on the equilibrium point, we'll discuss the stability of the system. Thank you very much for attending. We'll be continuing from the next lecture.